Coming to second subclass, oxidases. Removal of hydrogen. Here acceptor is O2. Very important. You should remember here acceptor is O2. In before dehydrogenase, the acceptor is, what is the acceptor? B12 vitamin. Okay. Examples: cytochrome C oxidase. In electron transport cycle, you all know about cytochrome C oxidase. Okay. In this red boxes, I have gave all the pathways. In green, I have gave only related to enzymes. You can see the enzymes. Okay. In the red boxes, pathways. Coming to first enzyme, cytochrome C oxidase. This is complex 4 in ETC. Okay. Cytochrome C oxidase. In the name, oxidase is there. Means here electrons are removed and added to oxygen. As you all know, in ETC, along the membrane, the electrons and hydrogen is added to the O2. So this example comes under oxidase. Coming to second example, monoamine oxidase, MAO. In our body, there are two types of MAO, MAOA and MAOB. Okay. You can see here the synaptic junction, now terminal part. Okay. Here we know the neurotransmitters are released here in synapse. Neurotransmitter 5-HT means serotonin, noradrenaline. These neurotransmitters released from here are converted into monoamines with the help of the enzyme MAO, means monoamine oxidase. This reaction is catalyzed by MAO. Coming to the clinical importance. Okay, clinical importance of this reaction. We know that antidepressants inhibits this MAO enzyme. Okay, it blocks this MAO enzymes. When this MAO is blocked, what happens here? MAO is blocked, the 5-HT is not converted into monoamines. Then this 5-HT and Ne will increases. See, in the red color I wrote antidepressants. It is blocking the MAO. So in red color here increasing serotonin and noradrenaline. In this way, in our brain, these neurotransmitters, if they are decreased, it will cause depression. Okay. Now due to this enzyme blocking here, these are increased. So these are used as antidepressants. Okay. This is the clinical importance in pharmacology. You can write this clinical point also. So as a doctor, when a patient comes with the depressant, you know the underlying mechanism, how you are treating that patients. Okay. Coming to the oxygenase. Oxygenase, these are two types, monooxygenase and dioxygenase. Mono, single oxygen atom, di, double oxygen atoms. Okay. This monooxygenase enzyme is also called as mixed function oxidase. Here see oxidase, oxygenase. You just remember this mixed function oxidase. That is the reason I put a tick mark here. Those you have to remember. Okay, this is not oxidase actually, but another name of monooxygenase is mixed function oxidase. Remember mixed function oxidase. Coming to dioxygenase. Okay, this is two atoms of oxygen. Here in again monooxygenase we have hydroxylases and cytochromes. This indicates that monooxygenases are more common here. Okay, in hydroxylases, here most hydroxylases. In monooxygenase we have hydroxylases and cytochromes. In that mostly hydroxylases we have. That is the reason we have nearly 5 types of hydroxylases. Okay, I will explain it later. Coming to dioxygenase. In dioxygenase we have homogentisate dioxygenase. Okay, tryptophan dioxygenase. I will explain this all later in the next page. Okay. Coming to monooxygenase. In monooxygenase, first we know that hydroxylase is most common. In hydroxylase, first one is PAH, means phenylalanine hydroxylase. These enzymes comes under tyrosine synthesis. This is very important reaction. You all know tyrosine synthesis. Phenylalanine is converted into tyrosine. Tyrosine synthesis. Tyrosine is synthesized. In this reaction, phenylalanine hydroxylase. What is happening here? You can see the green colored first. In green color, BH4 is tetrahydrobiopterin is converted into BH2. Dihydrobiopterin. The BH2 is again converted into BH4, converting NADP into NADPH. When you see the green colored, only green colored dot indicates the enzymes and coenzymes. See, these are coenzymes, BH4 and NADPH. These are coenzymes. This is main enzyme. Here you can see NADPH, okay, and hydroxylase, monooxygenase. This is monooxygenase. Monooxygenase is acceptor is oxygen atom. You all know what is the meant by oxygenase. Oxygenase means adding of oxygen atom. Monooxygenase means this reaction comes under adding only single oxygen atom. So in this reaction, one single oxygen is added to the tyrosine. Okay, if we elaborate the molecule, we can see that. You can check in your books. Okay, coming to tyrosine, we can see that tyrosine only enters into the metabolism actually. So phenylalanine is converted into tyrosine. Then tyrosine enters into metabolism in two ways, anabolism and catabolism. Phenylalanine directly cannot enter into metabolism. That is the reason phenylalanine need to be converted into tyrosine. Then tyrosine will proceed further. Okay. In this enzyme, coming to clinical point. Okay. When the PAH is deficient in our body, PhenylKetonuria 1 type 1 is there. Okay. Phenylalanine ketonuria, PhenylKetonuria, PKU type 1. Here you can see when BH4 synthesis is deficient, we will get PKU 2 and 3. When dihydrobiopterin reductase DHB is deficient, we will get PKU type 4 and 5. You can see here PKU is totally 5 types. First type is deficiency of main enzyme PAH. Second and third type is, and fourth and fifth type is deficient because of coenzymes. One is due to BH4 and another is due to DHB. Okay, you can just remember these deficient enzymes about these diseases. Coming to clinical manifestations of PKU, what will happen when the clinical manifestation patients comes with which kind of symptoms to you as a doctor, as a physician? You can identify this deficiency in the patient. I will discuss it later. Okay. Coming to tyrosine hydroxylase. Okay. Tyrosine hydroxylase TH. This is also hydroxylase. This is second example. First one is phenylalanine hydroxylase. Second one is tyrosine hydroxylase. Tyrosine hydroxylase, we can see the pathway. Catabolic fate of tyrosine. Okay, catabolic fate of tyrosine. Here we can see the tyrosine can only enters into metabolism, anabolic and catabolic. Now we are discussing the catabolic phase of tyrosine. Okay, catabolic phase of tyrosine. You can see here tyrosine is converted into dopa dihydroxyphenylalanine. Hydroxylase, what is the function of hydroxylase? What is the mechanism? You know, oxygenase. Hydroxylase comes under oxygenase. What is meant by oxygenase? Adding the oxygen atom. This is the reason I underline with green color. You can see oxygen is added. From where it is added? From tyrosine. From tyrosine to another substrate, oxygen is added. When oxygen is added, this is called as hydroxylase. In this way, you can easily remember the enzyme by seeing the reaction itself. Okay, you need not remember any enzyme. Every enzyme has a mechanism. You can just see the reaction and you can write the enzyme name if you forgot in the exam. So in the catabolic fate, it will happen. In the same way, second example, third example, tyrosinase. In tyrosinase also converts into dopa. This is both reactions are getting common product called dopa, dihydroxyphenylalanine. In this way, these two enzymes are utilized. This dopa is converting into catecholamine and melanin. That is the reason the catabolic fate of tyrosine is catecholamines and melanin. Okay, that is the reason these tyrosine hydroxylase and tyrosine are used in catecholamine synthesis and melanin synthesis. Coming to catecholamine, this happens in kidney, adrenal gland. Okay, adrenal gland, adrenaline. In sympathetic ganglion, noradrenaline. In melanin, iris, skin, hair, we have melanin pigment. Black color iris, skin, hair color due to the pigment of melanin. This is sensitized by these two enzymes. Okay, clinical points. Coming to clinical points, we can see in PKU what will happen. In PKU, in phenylalanine, when this is deficient, phenylalanine does not convert into tyrosine. Okay, when phenylalanine does not convert into tyrosine, tyrosine doesn't enter into the metabolism, thereby it cannot enter into catabolism. Thereby this catabolic fate of tyrosine is stopped. When this catabolic phase of tyrosine is stopped, what will happen? These further steps will not take place. So the catecholamine synthesis and the melanin synthesis will be inhibited. When the catecholamine synthesis is inhibited, what will happen? The neurotransmitters will be lost, so we'll get neurosymptoms. In this way you can easily understand the mechanism and identify the clinical manifestation. Neurosymptoms like agitation, anxiety. Where the patient comes with neurological symptoms, you can suspect or there is a chance of this enzyme deficiency. That's why in the PhenylKetonuria means the deficiency of phenylalanine hydroxylase, you will have these neurological symptoms in this way. In the same way, when melanin is deficient, we'll have hypopigmentation. Okay, so in phenylketonuria you will have both neurosymptoms and hypopigmentation also. Okay, in this way, by the mechanism itself, for any enzyme deficiency, by the mechanism you can easily understand the symptoms. Okay, now you need not remember the symptoms of phenylketonuria as neuro and hypopigmentation. If you just check the metabolism, if you can understand this. Due to the deficiency of that enzyme, this both synthesis is inhibited, then the symptoms will appear. Okay, coming to another point, when tyrosine, in tyrosinase is, if tyrosinase is deficient, what will happen? Minus means deficiency. When tyrosinase is deficient, we will again get the same problem. Melanin synthesis is stopped, then we have hypopigmentation called as albinism. So this condition is called albinism. Okay, this is the clinical importance of this. And fourth example, tryptophan hydroxylase. Tryptophan, so we can see this in anabolic fate of tryptophan. Before, previously we have discussed the tyrosine anabolic and catabolic phase. Now coming to anabolic phase of tryptophan. In tryptophan we get, as it is anabolic fate, we will get synthesis of tyrosine and melatonin. Okay, in melatonin, tyrosine and melatonin synthesis. See, anabolic fate of tryptophan, we get serotonin and melatonin. You know that in tyrosine catabolism we got melanin. Okay, melanin, that is melanin. This is melatonin. Okay, tyrosine, melanin, tryptophan, see I have rounded this, tryptophan, melatonin. You can remember like this. In tyrosine metabolism we get melanin, not melatonin, it is melatonin. Okay, coming to reaction, tryptophan is converted into 5-hydroxytryptophan. So hydroxylase, you can see hydroxylase group here. Okay, hydroxylase comes under monooxygenase, means single oxygen atom is added. See, I underlined in green color, single oxygen atom, I rounded. Single oxygen atom is added from substrate to product. So it is, this hydroxylase comes under monooxygenase. In this way you can remember this. By seeing the reaction, you can just write hydroxylase beside the substrate tryptophan. Now coming to this tryptophan, in this enzyme the coenzymes are NADPH and THB, tetrahydrobiopterin. Okay, you can just remember, like in anabolism you get THB, in catabolism you get PLP. PLP means B6 pyroxine. Okay, I'll explain later about this catabolism. This is the anabolic fate of tryptophan. In catabolic fate of tryptophan, coming in next page, we will get the catabolism, we get the sub coenzyme PLP. In this way you can remember this both, anabolism THB, catabolism PLP. Coming to this 5-hydroxytryptophan converts into 5-hydroxytryptamine. You remember, see I underlined this, fan amine. Tryptophan is converted into tryptamine. This tryptamine is called serotonin. It is nothing but serotonin. 5-HT, 5-hydroxy H, 5-hydroxy H, 5H and T. 5HT is serotonin. Okay, here the enzyme is decarboxylase because the carbon dioxide is released in this enzyme, but this decarbylase comes under lyase, which is class 4, not hydroxylase. Hydroxylase is not class 4. Hydroxylase comes under monooxygenase, which is a subclass of first class oxidoreductase. So it comes under first class. It is fourth class lyase. It is decarboxylase. Okay. We will get that later in decarboxylase. Okay. While getting to this tryptophan, this serotonin, it is degraded into indolestic acid 5-hydroxy. You can remember while reading metabolism. And it is also in pineal gland in brain. It is converted into acetyl serotonin, and acetyl serotonin converted into methyl acetyl serotonin. You can remember this later in metabolisms. Okay, these all. Now just remember that this methyl acetyl serotonin is nothing but melatonin. Okay, this acetyl serotonin converting into methyl acetyl serotonin. This is nothing but melatonin. This same serotonin here is degraded and is entering into, it is in brain, it is converted into melatonin in this pathway. Okay, in this way serotonin and melatonin is synthesized. Coming to the fifth example, 7-alpha hydroxylase. In this monooxygenase, this is the fifth example. I am giving many examples because these examples are very important examples in the very important metabolisms like tryptophan, tyrosine and cholesterol. That is the reason I gave many examples here. In this way we are covering the all reactions in every major reaction. 7-alpha hydroxylase, 7-alpha H. It is in liver. You can see in liver the cholesterol degradation takes place. Cholesterol in our body, it is converted into hydroxycholesterol, and hydroxy is cholesterol converted into primary bile acids. You can remember these names later, cholic acids and quinol deoxycholic acid. These are primary bile acids. So 7-alpha hydroxylase is useful in synthesis of bile acids, which are formed due to degradation of cholesterol. What is meant by degradation? It is catabolic fate. So cholesterol catabolic fate or degradation, or we can tell it as excretion. Remember this. Okay, remember, in cholesterol degradation is nothing but excretion of cholesterol. In our body, the cholesterol is excreted in the liver in the form of primary bile acids. In this way you can understand the concept by this reaction. In that reaction 7-alpha H is useful in this. Okay, the coenzymes are NADPH, O2 and vitamin C. You can remember it later, but in this main point is you can see the green color here. Okay, it is related to enzyme, means hydroxylase. What is the meaning of hydroxylase? Hydroxylase comes under monooxygenase, so oxygen is added. Okay, here oxygen is added. Okay, coenzyme. Coming to dioxygenase. Okay, dioxygenase, we have first example, homogentisate dioxygenate. In homogentisate dioxygenase, it is actually utilized in the degradation of phenylalanine or tyrosine. You know that we already completed the catabolic fate of tyrosine, in which we got two main products like catecholamines and melanin. Here again the catabolic fate, another product is also formed in the same tyrosine or phenylalanine catabolism. That is, we are getting here ketogenic and glucogenic fate. Okay, in the same way this is in the tyrosine catabolism. In the tryptophan catabolism you can see glucogenic and ketogenic fate again. So in this tryptophan catabolism and tyrosine catabolism you can see the ketogenic and glucogenic phase. You can see here. Okay, this is one of the step in tyrosine catabolism. Previously we already know the tyrosine catabolism have melanin and catecholamines. Okay, and tyrosine catabolism also forms thyroid hormones. Of course these four are the catabolic products of tyrosine. Coming to reaction, we can see here PLP. Okay, PLP is pyridoxal phosphate, which is coenzyme. Pyridoxal phosphate, vitamin B6. In this way we can know here deficiency, you can see here, homogenesis converting into mallyl acetate. You can remember these reactions later. The main, you can remember the clinical point here, very important. Clinical point, deficiency of this enzyme causes Alkaptonuria. Very important clinical syndrome or disease. Alkaptonuria, what will happen? In Alkaptonuria, when this enzyme deficiency is there, what will happen? This homogenesis is not converted into MAA. Then this homogenesic acid or homogenesis, both are same, HGA, this will increases in body when this enzyme is deficient. When this increases, what will happen? You can see here, this homogenesic acid is converted, is also excreted in urine. Okay, so this urine is colored black, and black or sometimes red color in infants. This is the clinical symptom you can observe. This homogenesic acid also will enter into the cartilages like nose, pinna, and also intervertebral disc cartilages. So we get back pain. The patient comes complaining you with back pain. This process is called ochronosis, means pigment accumulated in intervertebral discs in vertebra. So this back pain is due to ochronosis, okay, due to pigmentation, and in the nose and pinna we'll get black spots, you can see in the patient. In this way, the clinical is very important. 3 stars means very important here. You can remember this simple 2 or 3 points regarding this, enough. Okay, you can see here tryptophan dioxygenase, this catabolic fate of tryptophan. You already know that catabolic fate of tryptophan, same like tyrosine, we get glucogenic and ketogenic fate. Here again you can remember this later. Main points is got in red color. Okay, in this red color you should remember. Okay, here you can see the clinical point here. Clinical point, see, B6 deficiency. PLP is nothing but vitamin B6 deficiency. This PLP is a coenzyme. See in green color, coenzymes NADPH and PRP. This PLP, if this deficient in our body, if we have deficiency of vitamin B6, okay, a doctor will suggest us to take the supplements of vitamin B6. When the vitamin B6 is deficient, what will happen? You can see here, this kynurenine, N-formyl kynurenine, actually it is converted into many steps, and later this all steps you can read in later in metabolism, many steps, and later it convert into glucogenic and ketogenic phase. In middle, what will happen? This N-formyl kynurenemia, okay, N-formyl kynurenine, okay, kynurenine. This N-formyl kynurenine is converted into 3-hydroxykynurenine in middle somewhere. This 3-hydroxykynurenine will increase due to the deficiency of vitamin B6. When vitamin B6 is deficient, what will happen? This reaction does not take place. So this N-formyl kynurenine will increases. When this N-formyl kynurenine increases, it is converted into xanthuric acid, and this xanthuric acid is excreted into urine. That is the clinical point. This xanthuric acid you can observe in urine by making the urine test. Then you can tell that he is deficient in B6 vitamin. Okay, this is the clinical importance.